Okay, so today what we're going to do is we are going to talk about complex eigenvectors. And of course, this is where we left off before the midterm exam, and this is in section 3.4. And a lot of chapter 3 so far was devoted to finding eigenvalues and their corresponding eigenvectors. And I think it's worth rehashing why it is we devoted so much time to that. Well, one of the reasons is the eigenvectors of a system matrix, and in this case, we're looking at systems of the form of x prime equals ax. That is, it's a homogeneous linear system. First order ODEs. And the eigenvectors of the system turn out to be the limiting behavior of the general solution. And in the eigenvalue problems that we did, we were looking specifically at limiting behavior that gave lines, right? So if we had some vector field out in space with our equilibrium solution passing through the origin, the limiting behavior usually, in this case, happened to be lines. So our curves might look something like this, or perhaps they're going towards the origin. But nonetheless, eventually at some point, our trajectory curves will approach the lines and possibly even the equilibrium solution, which for a homogeneous system is always going to be at the origin. And we have actually a nice interpretation for this. So I'm going to go to MATLAB to kind of demonstrate why it is we care about this. One of our interpretations of the linear system x prime equals ax was a operator interpretation. So the right-hand side, a times x, can be thought of as the matrix A operating on a set of vectors x. So if we present the matrix with a set of vectors, the matrix is going to perform an operation on those vectors where some of them will be rescaled, so they're either stretched or shrunk, and some of them can be rotated in some sort of way. And I have posted a demonstration that illustrates this operator interpretation, as well as illustrating the limiting behavior of the eigenvalue problem. So in this demo, what I've done is I've created a set of vectors here representing a set of approximately all possible directions. And each of these vectors are starting from the origin 0, 0. And the scroll bar down here represents how many times we're going to operate on this set of vectors. And the matrix that I chose to use for this was the matrix A equals 3, 1 in the first row and 1, 3 in the bottom row. And what I would like to do is operate on this set of vectors and see what this system matrix does to it. So if I operate once, this is what we get. You'll notice that the vectors pointing in these directions here have shrunk down a little bit, or maybe a better way of saying that is they've been attenuated. Whereas vectors pointing along this direction appear to have been stretched. And if I want to continue doing this, I can operate on this vector field now, again using my matrix. So if I multiply by A, this is what we get after operating on the vector field twice. Again, vectors along this direction appear to be attenuated, whereas vectors pointing along this direction appear to be stretched. And if I continue on doing this, that behavior continues until we're pretty much left with vectors that are only pointing along this direction. And as you might have guessed, the vectors that point along this direction represent one of the eigenvalue solutions, right? So this would be one of the lines in our vector field. Whereas vectors that were pointing along this diagonal here are pretty much attenuated out. So that represents another set of eigenvalue solutions, but in this case, they're going away. And why do we care about this? So again, here's our original vector field. And whoops, we went a little too fast there. Here's our original vector field. And again, as we repeatedly operate on our vectors, here's something that we get. So coming back to our vector field interpretation, we can see how this operator interpretation, AX, might come into play. So suppose we have a vector field that looks like this, and also suppose we have some initial condition out here, say right at that point. And we know that our trajectories will look something like this as we go through our field. And as I suggested, eventually this will approach the limiting behavior of our system, which we showed was an eigenvector, one of the eigenvector solutions. Now, where does this matrix operation of repeatedly operating on a vector x appear? So in a discrete sense, we can kind of see how this actually might work. So if here was our initial condition and we're right at this vector, and we perform an operation a times x, well, what's that going to do? Well, it'll advance us out to perhaps some point out in space, and what we encounter is a new vector. So in going from sort of this point to this point, our system matrix has translated us from a vector that points like this to a vector that points like that. The only difference between these two vectors in our demo is that their tails are at different locations. So in the demo, I forced all of the tails of all the vectors to be at the origin. And here they're at particular locations in the phase plane of AX equals x prime. So in a discrete sense, the matrix A has taken this vector and it's rotated a little bit in addition to translating our location. Okay? And we can imagine performing that again. So we start with this vector, multiply it by A. It, using Euler's method, of course, it translates us out over to here. And the matrix A translated a vector that points slightly down and to the right to a vector that's pointing slightly up and to the right. So our trajectories can be thought of in this sense as repeatedly multiplying the vectors that we encounter along the path until eventually they're going to approach this eigenvector solution in this case. So eventually, as we keep repeatedly multiplying it, what we're going to end up with is a vector that points in this direction. So, and that's one of the things illustrated by our demonstration, and that's one of the reasons why we care so much about the eigenvector solution. Another reason that we care about the eigenvector solution is that for a 2 by 2 system, the eigenvectors form two linearly independent vectors, hopefully, from which any solution that is in the big set of all possible solutions that satisfies the differential equation can be generated. So our general solution can be rewritten in terms of the eigenvectors of your system matrix. And our general solution looks something of the form like this. Note, in this case, the eigenvalues come in right up here. These turn out to be the rate constants in the solution. So, some questions from here. Okay, question 1. Can we have complex eigenvalues? Okay, or eigenvalues slash eigenvectors. And we know that, of course, the eigenvalues come from the characteristic equation of the thing, of our linear system. The characteristic equation, of course, looks something like this for a 2 by 2 system. And we know that this is going to be quadratic, and it is possible to get complex eigenvalues from a quadratic equation. So our first question here, of course, is yes, we can have complex eigenvalues and eigenvectors. Another question we might ask is, can we have limiting behavior that is not a line? So can we have eigenvector solutions which of course represents the limiting behavior. That is not a line. And of course the answer to this is yes, you can have different limiting behavior. And of course, this is where we left off before the exam. And we looked at what happens when you get complex eigenvalues and eigenvectors, and what that does to the trajectory curves in the vector field of your linear system. Okay. So before we, so this is now 2 weeks ago, before we stopped for our first exam, we were looking at the following system. And this system has complex eigenvalues. So we found that the eigenvalues, lambda 1 was minus 1/2 plus I, and lambda 2 was minus 1/2 minus I. Okay, and just an observation of here, lambda 1 is the complex conjugate of lambda 2 and vice versa. Okay, we also found, and you can show this for review, so for homework, show this. the corresponding eigenvectors look something like this. So v1 was equal to 1i, and v2 was the vector 1, negative I. Okay, and also observe that these two vectors are the complex conjugates of one another. In fact, if we only wanted to find one, the other ones come for free, provided that all of the elements in the system matrix are real. So if they're are real, then we can immediately get V2 by taking the complex conjugate of V1 in this case. So it follows from this that the general solution to the system x prime equals ax is c1 e to the lambda 1 times t, so that's negative 1/2 plus I times t, okay, times v1. Okay, and then that's going to be the linear combination with c2 e to the lambda 2, which is negative 1/2 minus it times v2. And this is our general solution.